In this tutorial, we are going to see how to simulate a Verilog code using Xilinx ISE software. If you have installed Xilinx in your system, then you can see shortcut icon on your desktop. There you can double click that, else go to Start menu, go to Programs, there locate where Xilinx ISE is. There project navigator, you just click. This is one way. The other way is on desktop, shortcut icon, double clicking that. You can open that application. So once the application launch, you can see tip of the day, the pop-up. You can disable this one by unchecking this show tips at startup. Click OK. Here are the four windows. One is sources window, wherein you will see all your HDL files. The other is a processes window, wherein you will be having synthesize, implement, design, all these activities that you can perform on your HDL file. This is the transcript window, wherein you can have, if you perform any operation over this your HDL file, maybe synthesis, maybe implement design, maybe generate programming file related to this. If there are any messages, those messages are displayed here in console tab. In this transcript window, we have several tabs. In console tab, you can see all these messages. Specifically, if you want to see error messages, then click errors. If you want to see warnings, click warnings. Now here, this is the working area. Working area related tabs can be seen here. So let us go to, this is the menu bar. Go to file to create a new project. Click on file, click new project. This will open a wizard. Type your project name here, half adder HA underscore adder underscore DF, data flow level modeling. Here except C, in any other drive you work, because in C system files will be there. Accidentally you may remove, so better to work in some other directory. Click next. Here you have to set your target board. So we have the target board, that is family, Spartan family. So we have different FPGAs, CPLDs. So in laboratory we have Spartan 3E family. In this there are several other devices. So 100E to 150E, E stands for 1000. 100,000 logic elements device it is, Spartan 3. There is other variant of that. We have 500,000 logic elements here. Packages, several packaging technologies, all these are IC packaging technologies. So FG320 is the packaging technology that is there for this Spartan 3E device. Speed, the more the minus number, the more the faster it is. Synthesis tool, Xilinx synthesis technology tool we are using. Simulator, ISE simulator, this is the inbuilt simulator. Third party tools also we can use. Click next. If you want to create a HDL file, right here you can create. Later on, if you want to create, click next. If there is existing file in your system drive, then click add source, else click next. This is the design project summary. Click finish. Now, in order to write a Verilog HDL file, being in the sources window, you can right click and then select new source. This will open a wizard, new source wizard. This is one approach. The other approach is, being in processes window, you can double click this, create new source. same wizard will come. So third approach is go to menu bar, go to project, their new source. This is the third approach. So my approach will be here, bring in sources window, right click and then select new source. Verilog module, select Verilog module. File name here is HA, file name that is half adder. Ensure this is checked here, add to project, click next. Here port names you can give, later also you can give. So we'll be practicing later. So that is click finish. So here in this working area you will have two tabs. One is design summary tab, HA, that is file what you have created. So by default tool will generate a module with the name HA, what the file name you have given, with the same name it will create a module. So let us describe our half adder. A comma B comma sum comma C0, and then here input is a keyword. We have listed port identifiers here, and port identifiers to which port type they belong, that declaration is carried out with the keywords input and output. Input A comma B, terminate with a semicolon. Output sum comma C0, terminate with a semicolon. Here assign, that is data flow level modeling, sum equal to A XOR with B. For XOR, that is the symbol. Assign is a keyword in a data flow level modeling. CO is our identifier, that is for carry out. A ampersand B. Ampersand is a for AND operation, it's operator. So let us zoom this one bit for visibility purpose. So it's more clear now. This is comma, remember this is A comma B comma sum. So you can go to view there for zoom in F8, for zoom out F7. So let us F7. So comma is now it's clear. Now we have done our description. We have to ensure that this is the correct description. This is done through testing it by writing a test bench. For that, go to sources window, right click, new source. Select Verilog test fixture, and the file name here is HA_TB, half adder test bench. Ensure this is checked here, click next, click finish. This will generate a template. Remove this template. Now backport time scale, I will tell you later on what is that backport time scale is. 1ns-1 keys, enter, time scale it is. Module, and here file name you have given HA_TB, same name you give. Module name. In lower version this is the problem. Convert all inputs to reg type. Test bench we have to redeclare all inputs with a reg keyword and all outputs with a wire keyword. That is the syntax. Now we have to instantiate. See, these are the tabs. You switch in between the tabs. Go to this HA, copy this module along with port list, get to the test bench, here paste it, HA, that is the module name, in between port list, module name and port list, in between you write a instantiation name. Now here start giving the test vectors. Initial is a keyword, that is the procedural construct. Initial, begin. Here hash 5 within flower brackets braces a comma b, assign them with a 0. Here hash 5 is a time unit, so and the real time here associated is with a nanoseconds, 5 nanoseconds. Precision here is, instead of hash 5, if there is a 5 point something 78946 like that, so here 1 picosecond is the time precision. It tells the compiler what is the precision of a decimal point. So point 0.001 nanosecond is the time precision. So after decimal point, how many digits are there in that? 0, 0, 1, 3 digits. So compiler will retain after decimal point 3 digits. 436 is not shown in simulation result, only up to 5.786. So that is the time precision. Now I'll copy this one here because I'm going to paste 3 more times. Control C, and then going to change the value, assignment value. So here Control V, enter, Control V, 3 times. Here 1, here it is 2, here it is 3, and then here hash 10 dollar finish. This is simulation control system task, dollar finish. So terminates the simulation, and then end module, end module. Now this is cumulatively added up time. At 5 nanoseconds, AB is assigned with 0. At 10, AB is assigned with 1. At 15, AB is assigned with 2. Like that, cumulatively added up this time. Internally, if my operating system is of 32 bits, then this 2 is converted to 32-bit binary. So while assignment is carried out, from LSB side assignment will be carried out. Since AB are scalar type, put together they can hold only 2 bits. So if you convert this 2 into binary, then 1 0. So this 1 0 assignment is carried to AB. A will get 1, 0 is to B. Like that. Save this one. Now in sources window, sources for drop down menu, select behavioral simulation, select your test bench, come to processes window, expand this one, check syntax first. Now simulate behavioral model. If syntax is correct, you can simulate behavioral model. So this is because of the dollar finish. Want to terminate? No, we don't want to terminate, we want to see that one. So click no. Here is additional tab, see in a working window. Click that tab. These are the results. Select the marker here, single marker, once click, so cursor will be with this shape now. Place here at 8.1 nanoseconds, these are the values. Just click this one, hold left mouse button, drag it anywhere. So at 22.6 nanoseconds, these are the values. Since we are convinced with our simulation results, now we can go to synthesis. You can come to sources window, there are sources for drop down menu, select synthesis, and here you are not seeing any processes here. Click here processes tab. Now you can see all this. Expand the synthesize, run view RTL schematic. If you run RTL schematic, you will see the gates. A black box will come. If you double click inside logic gates, you can see. If you run the technology schematic, in your target board, you have, in your target device, you have some resources. So how many resources been consumed, which resources? So that graphical view we can see if you run the technology schematic. So but top level same, but if you double click inside you can see the variations. This is the lookup table for implementing this carry out. This is the lookup table. Inside this is the logic. Truth table you can see kind of map to implement sum. So this concludes our first tutorial, that is on simulation.